Yeah, hi, so I'm Jeffrey Sewell, and I'm going to talk a little bit about, so we're not going to so much shift gears as stop the car, get out of the car, get into a different car, and go down a different road for our presentation. If I've learned anything about working with big data, and analysts of all sorts, it's that there's a wide range of topics, specialties, and needs in this industry. So, who am I? I'm Jeffrey Sewell. I've been doing wireless and wireless data for about 15 years now. In 2011 or so, I started working specifically around the Hadoop ecosystem with HDFS and Hive and Yarn, eventually MapReduce, and then Spark starting somewhere around 2013 or 14. One of the key things that I needed to do during my years at T-Mobile, and until about a month ago I was a principal architect at the T-Mobile, was deal with data at this size with these algorithms, but on premises, not in the cloud. And so I want to talk a little bit about that today, specifically around the tuning, the configuration, the deployment. So why would you do on-prem versus in the cloud? Most of you here, and most people I've worked with, have dealt with Spark and big data and algorithms using Databricks. Azure is becoming very popular too. But there's a lot of reasons that we would stay on-prem. The biggest one, and the one that mattered at T-Mobile, was security concerns. There's a lot of data, and something like an S3 bucket tends not to have a whole lot of layers of security you can work with, and a lot of management gets anxious with that and asks you to stay on cloud. Another thing that also mattered at T-Mobile is the investment in existing servers. You know, when you've had data centers for a decade or 2 decades, you have a lot of hardware stacked up in there that people tend to want to take advantage of. And then control, and this was not so much the issue at T-Mobile, but a lot of people I've worked with over the years. You have a large investment in operational systems, in support, and people. You want to keep that control. And in a lot of ways, a Databricks type cloud solution provides you a black box. I'm going to go into some of the stuff that is inside those black boxes, but they provide you a black box, and there's not a lot of knowledge about exactly how your code, your algorithms are being worked underneath the hood. Some of the downsides, yeah, if you have the hardware, that's pretty good, but you have to take care of it yourself. I'm going to talk a little bit about that and about how some of this more raw approach to your data can be done. But there's some ups and downs. So let's talk briefly, and I apologize for any of you who might find this somewhat redundant, but I want to go over the 2 main distributed platforms that we do Spark and machine learning on, and that would be Yarn and Mesos. So we do Spark on Yarn. This is just to level set everyone about what the discussion is. But you start with your edge node, right? You run your submit, and then the next thing that happens is that this piece called a resource manager, and if you set it up yourself, you need to know what this is, you need to build it, is going to start talking about your job. And it's going to open up a Yarn node manager and call it the application manager, because manager is a very important word in this conversation. This is all done in Java. These are all JVMs running inside whatever leftover hardware that you have for your on-prem solution. So it's pretty easy to set up. Well, now we get into the end of the presentation, apparently. Now we get into the container. So this is probably more familiar to any of you who know Spark, is you build that Spark driver. And it's all being run, again, by the node manager. And if you've ever done this at the command line, you'll recognize that there's little messages coming back. Well, that's fed back through this path, through the node and the resource manager. Once the job has been kind of laid out, your DAG is built, it'll go up and ask the resource manager, hey, what do I have? What are the systems like? What are CPUs? What RAM can I use for this? And it will respond, and then it'll send the requests out to them. Again, you have to talk to the node manager on each system. Once you do that, your containers are being built. Again, these are all JVMs. You have a heap, you have core CPUs that have been allocated. They start having a conversation of their own with the driver. And this is external of the Yarn distributed infrastructure. Well, when the job is finished and you've done all of your work, strongly recommend any on-prem solution have a Hive history server. This is where the results, the entire lineage of the job you ran is going to get stored so you can figure out what you did right and wrong later. Okay, so yarn. One of the biggest problems you find when you build yarn yourself is this thing called the maximum allocation. So what is that? This is the sample cluster I built. Down here, the maximum allocation, it says we have 8 gigs and 4 cores. But if you look at 2 of the nodes on the system, well, they have 16 and 32 gigs and 8 cores each. Why is that? And what can we do about it? Because if you submit a job to Spark in this environment and say that you want 8 cores, it will reject you. It says, nope, can't do that. That's because of this maximum allocation thing. And a lot of this gets kind of hidden. If you have a good operations team, they'll fix this for you. But if you're building it on-prem yourself, you need to be aware that you have to work around this. How to work around it. Here's the baseline submit. I'm going to show you some charts about how this ran. A basic submit, simple ag, yarn, and cluster. I will always recommend you put your jar someplace centrally located, because this data is going to have to get transferred across the network to every node. How do we solve this maximum allocation? Well, I want to run on 16 cores. Well, one way to do it is to break it out into 8 and 1, 1 executor core for 8 executors, or flip it and go 4 executor cores for 2 executors. Well, what does that do to your job and your performance? Well, let's have a quick look. These are the results of that baseline job run in the 2 environments. We have here 2 things that I want to call out in these graphs. So what we have is the memory and the CPU for these jobs. They're split into 2 phases with yarn. The setup phase, and this is the stuff at the top of the previous chart, where the job is being built, the resources are being allocated, and everything's being created. And then the actual run of the job. So you can see down here we have the run and the setup for the 2 different variations. Memory-wise, you can see immediately that this one server that did most of the work spiked up 50 to 80% on its memory, 70. Whereas when you did 4 cores, 2 executors, a much shorter jump. Same with the CPU. It's a faster spike versus a smaller one. So the setup here is a little more complicated because there's 8 executors. It has to build 8 different remote systems to run your code. Here, 4 cores, 2 executors, goes faster. Setup's shorter. And you can see it sort of bumps the other machine. We'll come back to this chart to kind of describe this, but we got better parallelism is the takeaway on this. Switching, and we had to do this, and I'm always going to be sorry about this. We had to switch at T-Mobile to forcing everyone onto 1 core. And we saw a big performance hit for doing that. But what's next with yarn? Well, what else do you want to do with it? Yarn has come a long way in trying to help parallelize all of your jobs and make them run faster. And the one key thing they added early on, I think, was shuffling. So what is shuffling? It's an external listener that you have to build on each machine. And this is going to listen for an additional request from your nodes, your executors, when they run. You have to set it up in the config file on each of the node managers. What it's going to do is when your job gets done with one stage, you have a bunch of data. That data may be lopsided, or server A will have 90% of it, server B only 10. Well, you don't want to run your next job, your next stage of your job, with that lopsidedness. So the shuffle service rebalances the data between. The problem is it goes over the network. And if any of you have seen the breakdowns of how fast things are in a computing system, network and disk are always the slowest. That's where serialization matters. Neither of these things are enabled by default. Highly recommend, always recommend enabling Avro or some sort of serialization so that when your data goes out over that network, it's a lot less data. Shuffling lets you do dynamic allocation. And I'll show some of this, and I know Tatiana has some things to say about it. Until recent versions, not super good. It does require shuffling, so that has to be enabled. I did find in my tests on 2.4.3, much, much better than it was in the previous versions of Spark. So let's do a little bit of graphing. So here's 4 different jobs. Same code, but 4 different submissions. Once again, we have the setup phase and the running phase. And here you can probably see a little better. The blue-green lines is the first system of the 2, and then the purple pinkish ones are the second. So we have a plain submission baseline. No frills, no switches, nothing. It does pretty well. kind of a small setup phase, immediate 25% spike on one system. And we look for both systems to be engaged to see how well parallelism is going. If you only see one as you will in a few of the others, it means it's not distributing the job very well. Here I enabled just shuffling. And there's a second little pre-spike here, a foothill, if you will, that is the job moving to the next phase. So at that point, you can see it actually brings up the second server and redistributes the data between the two. This is what we call 4x4. So this is getting around that maximum allocation problem. I submit it with 4 cores, 4 executors. And it gets me to the 16 that I want. Again, the spike's a little higher on the CPU. The memory, about the same. But you can see I forced it to bring in the second server. As an experiment, I added shuffling and told it to use 4x4. Didn't really do much. Not much of a change. I was even curious if shuffling would override the 4x4. It did not. 4x4 actually showed up in the logs and the requests. But the best one on this run was the dynamic. So this is just, you don't tell how many executors, you don't tell how many cores or memory, you just say use dynamic. And it did surprisingly well. It did not parallel because the code didn't need it. The data I was testing on didn't actually need 2 servers, and so it didn't bother. On larger jobs, it does a better job now. And then, as an experiment, I added the request for the 4x4, and you can see there it brought in the other server. But it didn't need to, and it is actually a higher spike, so this was not a great test, or not a great result. What are my observations? Well, Yarn is easier to set up. If you're going to build on-prem and can take this over yourself, Yarn's easier. As long as you have a Java home set, it's pretty straightforward. The configuration is just some XML that you have to build. The resources from each node, and this is an important difference, each node is going to register with the resource manager how many CPUs, how many cores, how much memory, and you can add GPUs and things there. Once it registers that, it doesn't update. It'll heartbeat, but it doesn't ever come up and say, oh, someone else got onto this box and started running a big bit mining thing, Bitcoin mining, and we can't use it anymore. That doesn't show up. It will actually ask for resources that are no longer available because it doesn't know. So that leads you to a lot of failed executors when you're in systems that are being used by multiple tenants. And yeah, the maximum allocation can throw developers off. Sometimes as you're running your jobs, you find people spin their wheels for days because they don't know they have to make these little tweaks, quirks of the way Yarn does this. But I will say that dynamic has come a long way. When we tested with dynamic at T-Mobile over the last year and a half, it was just terrible. It was much worse than using manually configured executors and cores and memory. Doing much better in 2.4. I'm actually quite happy with it. So let's switch over to Mesos. So Mesos is not JVM based. You have to compile it for each CPU that you want to use or use an RPM. This is the one that the people who wrote Spark first came up with. They built Mesos to run Spark in a distributed environment. So when you kick off a Mesos job, there's something always happening. And this is a key difference between Mesos and Yarn. The back-end systems are constantly updating the master with information about what they have. And so it's much more dynamic if your systems are being used by other processes. You'll get a better response out of Mesos. So you submit the job. This thing here, Mesos Spark Dispatcher, is another setup headache. It's a different process you have to run. It's independent of the master. You have to run the Spark Dispatcher, which is a framework inside the master. Again, just more overhead. Once you figure it out, it's not bad, but there's still a steeper curve. It will then register your job with the master for you, and then builds your driver. And it's not a JVM, it's actually a C++ container with a JVM inside of it. At the same time, it talks to these guys and sets up a bid system where it says, okay, I have this job with these requirements, who can do it? And the agents themselves will be the ones to tell you what they can and can't do. Once it has that information, it sends it back to the driver, and then the driver sends the tasks out to the, actually sends the task to the master, master back to the agents and says, build our Spark job. Once again, it's an executor that's custom and not the JVM runs inside of it. One of the things that's happened in the last few years is a move towards Docker, and replacing this piece with Docker. It's actually worked out pretty well. There's also, secondarily, a move from the Spark to natively run Docker for all of this. It was not really ready in 2.3. 2.4 has improved a lot. I don't think it would be production ready, but I think it's ready to start doing more tests. Same with Yarn. It reestablishes its own connection external of the management system, and then always, always, always have your history server. So with Mesos, this was the baseline. This right here is the IP address and port of the dispatcher, not of the master. It has to be run through REST, and once again, have an HDFS or an HTTP location for your jars. Saves you a lot of headache. How did it do? Well, first we have systems 1 and 2. Notice there's no setup. Mesos does this so much faster, it's pointless to even try and isolate the setup phase. It's just one phase. Baseline out of the gate does pretty well, right? So this is 40% where the other one was down, so the utilization's higher, but it parallelized much more quickly and had a much lower memory footprint. Using shuffle, once again, you have to start another service on each server for the shuffling to work. Less parallelization because the job didn't require it, but it still had more than we saw with Yarn. This is, instead of doing 4x4 with Mesos, you can just say, I want 16 CPUs. In fact, you should say you want 16, because if you don't, Mesos will give you all the CPUs. No matter how trivial your job, all the CPUs will go to it. That can be a bit of a problem, so always have a maximum and a required amount of CPUs for Mesos. Added the shuffle in, just to see how it went, roughly the same as 16. Really good results from the dynamic. A lower peak, another peak and valley peak because the shuffling event, and didn't even use the second one, because again, it doesn't need to. It only uses it if I force it, like here, where I did force it. And even in this one, it didn't use it initially, but after the shuffle, it added the additional cores that I told it to. Observations on Mesos. Well, it is harder to build. If you're using anything other than an Intel chip, you're going to have to build it. Even with Intel, you usually have to build it yourself because the RPMs are behind. There's a company that has a commercial version, Mesosphere with a DCOS. I can't say for sure, and I won't, but I suspect there's some relationship between them and not having the open source version updated very well. Yeah, the packages are usually not current. It was written for Spark, and it shows. The performance metrics are much better on Mesos. And yeah, the rumor that I've heard from multiple sources is that Databricks is using a version of Mesos under the hood for their cloud version. Once you build it, it is easy to set up. That is, the jobs. So configuring and building, not easy. But once the jobs are done, they build themselves much faster. And yeah, it's a better neighbor to other processes that might be running with its constant updating and reporting. So a few takeaways to end. Yarn and Mesos, well, I wouldn't use Yarn's dynamic until you get the most current version. Mesos' dynamic has been much, much better for a longer time. Kind of saves the developers, the data scientists a lot of headache trying to make their jobs run. When you do have large jobs, definitely want to use shuffling on Yarn. With Mesos, yeah, it'll do shuffling anyway, and if you add the cores, that's actually really important. Easier to set up in Yarn, yeah, JVM, and you're done. Harder to set up, yeah, if you want it in some environments, you have to build it yourself. But when the actual job runs, yeah, more overhead on Yarn. It takes longer to build the jobs and run them, and much less for Mesos. And the jobs themselves take longer to build, set up. So that is the truncated fast version of what I've got. Like I said, it's an interesting challenge to run this yourself. There is a wide spectrum of expertise and backgrounds in the world of big data and data science, from the people who know the algorithms and the business case to the people who actually make the code run. And a lot of times I find we have to kind of wear multiple hats. So hopefully this will be helpful in wearing the operator or the engineer hat when you have to do that. I'm done.